All right, here in problem number 5 and 13.6, we're going to apply some of those ideas from the last video on the geometric properties of the gradient. And so we're asked to find the directions in which the function increases and decreases most rapidly at p, then compute the derivatives of the function in these directions. And so for part A, we have the function f of xy is y times e to the negative x plus x times e to the negative y, and our point P is the origin. And over here, I've included just a couple level curves of our function, and they're pretty complicated. You can play around in Desmos to get a feel for what they look like, but notice here's our point P at the origin, and this level curve here in pink is the one of interest for us, right? It's the one that passes through our point P. And then c equals 1/2 here in green, and then c equals -1/2 in blue. All right, so what we were saying in the last video was that if I want to move in the direction of max increase, right, what I should do, moving from P, is I should head directly away from my level curve and head straight for this green contour, right? So I'm going to move in a direction that is orthogonal to this level curve. And we also proved in that video that the gradient vector is, right, orthogonal to that level curve. Sorry, orthogonal, perpendicular, remember, are synonymous, so I sometimes use one or the other. All right, cool. So let's go ahead and compute that gradient vector over here. So this will be just our partial f partial x and partial f partial y for the components. And so here, taking the x derivative, we'll get minus y e to the negative x plus e to the negative y. And then for the y derivative, we'll get e to the negative x and then minus x e to the negative y. Watch those negatives you pick up from the chain rule, right? All right, and so then we can go ahead and evaluate this gradient at our point P. So plug 0 in for both x and y. And there we're going to get a 1 and a 1. All right, so this is our gradient at our point P. And what we proved in the last video was that that is the direction of max increase. So that would be our answer for this first part. And furthermore, what we proved is that the maximum rate of increase, right, that's the directional derivative in the direction of the gradient, that is simply the magnitude of our gradient vector evaluated at our point. And so there we'll just take the magnitude of the vector 1, 1, and that has a magnitude of √2. Okay, so these would be our answers for max increase. Now if I want to think about max decrease, well, basically we want to use the same line of reasoning that we did for max increase, right? If I want to decrease at the fastest rate, right, from the point P, well, I want to move directly away from this level curve and head directly towards blue. And so in other words, I'm going to head in this direction that would be orthogonal to my level curve through P and head directly towards blue. So in other words, this would just be the opposite of the gradient vector. Okay, so we're going to head in the direction opposite the gradient at 0, 0. And so that'd be the vector -1, -1. Okay, and when we proved that the maximum rate of increase was just the magnitude of the gradient, right, we were really looking at the magnitude of the gradient times the cosine of theta, right, where theta was the angle between our direction of motion and the gradient. Well, now if I move in the direction opposite the gradient, right, the angle between my direction of motion and this gradient would be 180 degrees, and the cosine of 180 degrees is -1. So in fact, this rate of change would just be the opposite of the magnitude of our gradient. So -√2. Or put another way, this is a little bit more down to earth, right? Think about standing on a hillside, okay? If you're going to walk in the direction that is steepest, okay, so I'm walking up this hill at a rate of the slope of √2, okay? Well, if I want to, say, walk in the direction of greatest descent, what should I do? Well, just do a 180 and then start walking, right? And that slope will just be equal but opposite to the slope of maximum ascent. Okay, so yeah, that makes sense. Okay, so these are the answers for A. And for B, we're going to really just apply the exact same idea, except now the main difference is that we're working with a function of 3 variables. Okay, but all the same ideas carry over. Okay, so we'll first go ahead and just compute our gradient vector. We can do that over here. So this would be the gradient of the function rho at x, y, z. So this would be partial rho, partial x, partial rho, partial y, and partial rho, partial z. Okay, so let's compute each of these derivatives. So for the x derivative, well, I have an x in my log, so I'm going to do 1 over this thing. So x squared plus y squared minus 1 times the derivative of what's inside with respect to x. So that'd give me a 2x there on top. Then the rest of it would just be 0 because I don't have any x's in those other terms. Okay, for the y derivative, it's going to, for the log part, look just like the x derivative, except I'm going to have a 2y up there in the numerator. And then I'm going to do plus 1 because of the y there, and the derivative of 6z would be 0. And then the z derivative is nice, it's just going to be 6. Okay, so then evaluate this gradient at our point in question, which is P with coordinates 1, 1, 0. So here plug in 1 for x, 1 for y, and 0 for z. So what are we going to get? Well, our denominator would be 1 plus 1 minus 1. So our denominators are just 1 here and here. And then x and y are both 1, so I'm going to get 2 over 1, so 2. Then I'm going to get a 2 over 1, so again a 2, plus a 1 would be a 3. And then this k component is constant, it's just 6. Okay, so then the direction of max increase, well, that's just the direction of the gradient. Evaluated at our point. That exact same idea, the exact same proof carries over for functions of 3 variables. And what would be the rate of change of our function in this direction? Well, again, it would just be the magnitude of our gradient evaluated at our point. So this would be the square root of 2 squared plus 3 squared plus 6 squared. So what do we have here? That's 7, right? It's nice because it's 36 and 4 and 9, so it'd be the square root of 49. Yeah. All right. So then how about the direction of max decrease? Well, same idea as what we saw in part A. We're now going to move in the direction opposite the gradient evaluated at our point. So this would just be minus 2, minus 3, minus 6. We're going to head in this direction. And the rate of change in that direction, just like in A, would be just the opposite of the magnitude of the gradient. All right. So that is going to do it for this problem. All right. See you on the next video.